first of all, autonomic nervous system. Because we have finished the somatic nervous system, right? We had one session about the spinal cord, second session about the brainstem and motor cortex, today's session about the cerebellum and basal ganglia. So we have finished the somatic nervous system now. This part, the autonomic nervous system, which deals with functions of the internal organs. So, internal organs include several things, you know that, right? Stomach, intestine, colon, bladder, heart, everything. Everything inside inside the belly, the stomach, and we have also other organs, for example, in the head, in the neck, that are controlled by the autonomic nervous system. So, arterial blood pressure, GI motility, cardiovascular regulation, bladder emptying, sweating, body temperature, things like these are all controlled by the autonomic nervous system. And the autonomic nervous system is very fast and efficient in controlling these parameters. For example, in only a few seconds, it can increase the heart rate. It can double the heart rate. For example, from, 72 to more than 140. So in a few seconds, it is doubled. Or in a few seconds, the blood pressure can go down to like very low pressure, very low value, right? So, autonomic nervous system is very fast and efficient. And for autonomic control of the internal organ, there are two ways. One way is activation of the limbic system that controls some centers in the brainstem, in the spinal cord, and these centers can control internal organs, right? So, limbic system, centers in the brainstem and the spinal cord, and then they can change the activity of the internal organs. This is one way. Another way for controlling the internal organ is by way of some reflexes. For any reflex, we should have sensory information, then processing of the information, then motor signal, right? So the same also happens here. There should be some sensory signals from the internal organ. So sensory signals, then they go to ganglia, brainstem or hypothalamus. So these are some centers that control the autonomic nervous system. Then from here, we have motor responses that go back to the visceral organ. So for example, from the heart, there may be some signals that go to autonomic centers, then they come back again to the heart. So this way they can increase or decrease the heart rate or contractility.
Yeah.
Right?
Right.
So the motor part, the motor signal can go through sympathetic nervous system or parasympathetic nervous system. Right? So this was an introduction about the autonomic nervous system. Now let me compare somatic system with the autonomic system. In that side, you can see the somatic nervous system. So you know that motor neurons originate from ventral horn, right? Anterior horn or ventral.
Somatic.
Yeah, in the somatic motor system. They go directly to the skeletal muscles, right? They cause contraction. We know that. But what about autonomic nervous system? Fibers or neurons originate from the intermediate lateral horn
From the class
or lateral horn, intermediate lateral. They go to a ganglion, they make synapses there, they activate another neuron which is called postganglionic neuron, and postganglionic neuron innervate the internal organ. Right? So there in the somatic system you have one neuron, but here we have two neurons. somatic motor system, neurons originate from ventral horn.
هي
In
غنتاوي
the autonomic nervous system, neurons originate from intermediolateral zone. Right? There, in the somatic system, there is a classic synapse between the axon and the muscle fiber. Classic synapse means there should be an axon terminal, a synaptic gap, a fiber that respond to this neurotransmitter. Right? But here, we don't have a classic synapse. It's different. You can see that the axon shows some enlargement that is called varicosity. So varicosity is an enlargement of the axon.
So the function,
Inside the varicosity, we have vesicles.
the function of the
Yeah, I'm talking. Okay. So inside the varicosity, we have some vesicles. So they contain neurotransmitter. So they can release the neurotransmitter if there is action potential from the postganglionic axon. But it doesn't end here. It continues its path, makes another varicosity, so it can also release neurotransmitter. Then the axon continues its way. Right? Again, it may have the third varicosity, the fourth one, the fifth one. So an axon may have several synapses, not only one. Right? So this is another difference between the autonomic nervous system and somatic nervous system. The other thing is that here, in the somatic motor system, each axon terminal activates only one fiber or one cell. Right? This axon terminal activates this one activates this. So there should be one branch for every cell. But here, the varicosity releases neurotransmitter. It can diffuse in the environment. It can activate several cells, not only one cell. Right? Then the second varicosity excites another population of cells. The third one excites another population. So a very large number of cells can be activated or inhibited by the neurotransmitter that is released by the postganglionic cell. Got it? So there are several differences. One neuron here, two neurons here. Ventral horn as the origin, intermediolateral zone as the origin. Classic synapse, varicosities. Limited number of cells that are activated, a very large population of cells that are activated. Got it? So there are differences. And the main difference is this one, ganglion. So we have preganglionic, postganglionic neurons. Did you have any question?
Doctor, effectors in the previous slide, where is their location and their function?
Effector in this?
Yes?
Okay, it can be a heart cell, intestine,
blood.
stomach, eyes, everything. Okay? We are talking generally.
This enlargement can affect more than one cell.
Yes. Okay? Because the neurotransmitter is diffused in the environment, in the extracellular cell space.
Yes.
Okay? So now let's focus on the sympathetic nervous system. So we know that sympathetic nervous system originates from T1 to L2.
Always activation except the GI.
Always what?
GI mortality.
Okay. No, it always inhibits the GI mutation.
I say sympathetic always activated. Just in the GI motility, it will be inhibition.
Okay. So let's see. Okay? So, preganglionic neuron originates from T1 to L2. They go to the sympathetic chain. Sometimes they are called paravertebral ganglia. Paravertebral ganglia. They go there, some fibers pass the sympathetic chain and go to peripheral ganglia or perivertebral ganglia. So in sympathetic chain or in perivertebral ganglia, we have the cell body of the postganglionic cell. Right? So we have a synapse here or here. Postganglionic cell is activated. It sends the axon to the internal organs or the effector. So the effector can be intestine, can be stomach, liver, bronchi, heart, eyes, kidney, any of them. Right? So, what else? So you should remember the ganglia. Celiac, superior mesenteric, inferior mesenteric, or auricular, right? So now let's see the connection between them. Intermediolateral or paravertebral, perivertebral ganglia. So, in a cross section of the spinal cord, you can see intermediolateral zone. This is the origin of the preganglionic fiber. It originates here, sends the axon through the ventral root. So ventral root joins the dorsal root and makes the spinal nerve, right? So the axon goes into the spinal nerve, but soon it goes away. It exits the nerve. How? By way of white ramus, right? So the fiber, the red one, enters the sympathetic chain, paravertebral ganglia. It may end here, or it may go up or down and make synapses in any of these ganglia. Maybe this one, or some ganglia above, some ganglia down, right? Then, or maybe the fiber doesn't stop here and goes out of the sympathetic chain and enter the peripheral ganglia, perivertebral one. And it makes synapses with the postganglionic neuron in the peripheral ganglia. Postganglionic cell sends the axon to the internal effector. Right? So sometimes the postganglionic cell sends the axon back to the spinal nerve through the gray ramus. So white ramus for exiting the preganglionic cell, gray ramus for entering the postganglionic cell into the spinal nerve. So you should know this connection, right? So splanchnic nerve is a nerve between the sympathetic chain, peripheral ganglion, and the internal organ. We have also here sensory fibers, green one. It can sense the internal organ, so everything inside. For example, distension, pain, pressure, everything. Temperature, right? So sensory information goes through the axon, through inside the splanchnic nerve. They enter the sympathetic chain. They don't stop here. They go out through the white ramus, right? Enter the spinal nerve. They go through the dorsal root and enter the dorsal horn. Remember, the cell body is here in the D origin. So, in the autonomic nerves, we have postganglionic neurons, preganglionic neurons, and sensory neurons. So, splanchnic nerve, we have preganglionic, postganglionic, and sensory. Any questions so far?
The preganglionic in the white ramus is next three pathways or after internal ganglion? Yes, yeah.
This one? You mean this?
No, one is.
Yeah, this one, the red one.
Yes.
So, it leaves the spinal nerve, enter the paravertebral chain, right? Maybe it ends here, and the postganglionic cell, again enters the spinal nerve. So this is one possibility. Another possibility is going up or down and making synapses with postganglionic neurons in other ganglions. Again, they can enter the spinal nerve, right? Sometimes they don't end here. They leave the sympathetic chain, enter the peripheral ganglion through splanchnic nerve, right? They activate postganglionic neuron that goes to the internal organ, right? So it can end here, it can go up and down, it can go out of the sympathetic chain. So 3 different fates for preganglionic cell. Any more? No question? Okay.
Sensory neuron re-enter the spinal cord through gray ramos.
No. Sensory one to white. So it's better to say that the cell is here and sends the axon through the white ramus to the sympathetic chain, then through the splanchnic nerve to the internal organ. So this is the direction of the axon. But what about the direction of the signal? It's from here to this point. Okay? Okay, I told you that some of the fibers in the sympathetic nervous system enter the spinal nerve. So spinal nerve is a somatic nerve, right? It contains motor axons and sensory axons. We know that. Axons of alpha motor neurons, axons of gamma motor neurons, axons of sensory fibers that come from Pacinian corpuscle, Meissner, Merkel, all of them. So all of these are somatic part of the body, right? But here we can see that a few of sympathetic fibers also enter the spinal nerves. So around 8% of fibers in the spinal nerve are sympathetic fibers. So why they are important?
For blood vessels.
Yeah, they can innervate blood vessels in the skin. They can innervate sweat glands. They can innervate hairs. Right? So we know that spinal nerves are actually spread all over the body. Spinal nerves. We know dermatomes. Right? So there is a way for sending axons all over the body. So imagine that you want to also send sympathetic fibers to sweat glands. Instead of having another population of nerves, another 31 pair of nerves for sympathetic fibers, they use the same somatic fibers to reach the sweat glands. Okay? So the same way is used also by sympathetic fibers. Got it? Is that my point? Okay. So they innervate blood vessels, sweat glands, pyeloerector muscles.
So
Yes?
the sympathetic fibers use the somatic fibers.
Not somatic fibers, somatic nerves.
Okay, nerve. What about the signals? Doesn't interrupt together?
No. Each fiber has its own fiber signal. We had this actually before, right? So in a nerve, you may have thousands of fibers. Each fiber works alone.
Specific order of neuron.
Yeah. So there is a sheath around the nerve that covers the nerve, but inside the nerve we have a lot of fibers. They are separated. Right? So, preganglionic sympathetic fibers that innervates head area come from a T1 segment. So, from T1, fibers go to the head. From T2, they go to neck. T3 to T6 go to thorax. T7 to T11 go to abdomen. T12, L1, L2 go to clicks. So sympathetic fibers that innervate eyes come from segment. Sympathetic fibers that innervate the heart come from
T3 to 6.
T6. Right? Easy.
Doctor, sympathetic fibers that innervate our extremities are from T1?
T1,
Yes or not?
extremities.
T2.
So
Because
maybe T2, T3, T6.
because brachial plexus, okay, includes only T1.
Really?
Yes.
Yeah, this is pure anatomy, I don't know. Yeah, it's better to ask Dr. Hassan.
Is that correct to the somatotopic arrangement of them?
Somatotopic arrangement for this fiber? No. For sympathetic fibers, we don't have orientation or somatotopic orientation. Okay, so now let me mention again that internal organs are innervated by postganglionic sympathetic neurons. Am I right? So preganglionic from the spinal cord, come to the ganglion. From the ganglion, we have postganglionic neuron that innervate the internal organ. But there is only one exception, and the exception is the adrenal medulla. You know that adrenal gland has two parts, cortex and medulla. Cortex releases steroid hormones, right?
Right, yes.
Corticosteroids, mineralocorticoids, right?
Yeah.
But the medulla secretes catecholamines like epinephrine, norepinephrine,
So,
right? So the adrenal medulla is innervated by preganglionic sympathetic neurons, not postganglionic. So this is the exception, right? So I told you that from the intermediolateral zone, we have preganglionic neurons that go to the ganglion. They activate postganglionic neuron that send the axon to the organ. Imagine that this one is heart. Right?
right.
So internal organ is innervated by postganglionic neurons. Right? There is only one exception. So if we have adrenal medulla,
Yeah.
this one, preganglionic neuron
Yeah.
from here goes directly to the adrenal medulla without activation of the postganglionic neuron, and then postganglionic activate the medulla. Okay, so preganglionic neuron directly goes to the adrenal medulla. So
Just that exception? Just that exception?
yeah, there is only one exception, and it's this one. So intermediolateral organ cells, preganglionic sympathetic cells, sympathetic chain. Right? Splanchnic nerve, adrenal medulla, non-stop. Right? Without postganglionic neurons. So you can see that preganglionic sympathetic axons come directly to the adrenal medulla, active these chromaffin cells. They secrete epinephrine into the blood. So epinephrine here is not a neurotransmitter, it's a hormone. Got it?
Yes.
Good. Parasympathetic nervous system. So I told you that sympathetic nervous system originates from T1 to L2. Parasympathetic fibers originate from brainstem or sacral region, S2, S3, S4. right? So from brainstem, 4 nerves carry parasympathetic fibers. Nerve number 3, oculomotor, right? Nerve number 7,
Facial.
nerve number 9,
Nasopharyngeal.
nerve number 10,
Vagus.
weights. Right?
Right.
And
Glasses, sorry.
again we have ganglion. Ciliary ganglion for nerve number 3. Pituitary,
Number
nerve number 6. Submandibular, otic, line. Right? And for vagus we don't have specific. So, the vagus nerve contains more than 75% of parasympathetic fibers. So when we talk about parasympathetic system, we mainly mention weight. Actually, it activates or it can influence structures inside the thorax or inside the abdomen. Stomach, small intestine, colon, ascending, transverse, part of the descending. Right? But the second half of the descending colon is innervated by sacral fibers, sacral parasympathetic fibers. Question?
Doctor, 75% of all parasympathetic fibers are carried by vagus nerve,
Vagus nerve. The remaining 25%
by other nerves.
by other.
Doctor, vagus nerve have ganglion?
No, it doesn't have specific ganglion. So, neurons go to the internal organ, and on the wall of the internal organ, they make connections with the postganglionic cell.
But central, there is a lot of ganglion.
Yeah, there may be a lot of ganglion, so we have a lot of ganglion, right? But I don't think that we have different names for them. Do we have? Neuroanatomy?
We have two ganglion,
What are they?
spear and inferior ganglion of the vagus.
So they will give
Spiral.
But I think it's not enough. Or sensory.
Spiral what?
Spear and inferior ganglion of the vagus.
Do you mean olfact for elevation?
What?
There's ganglion.
He said.
Two ganglion.
So, there may be some ganglion, okay, but for example, the vagus nerve innervates the colon. Where is the ganglion?
There
I
are
think it's
Garden.
not related to us.
You mean there are no specific ganglion for
Yeah, I mean this.
covers the
Yeah.
garden and the
There's two ganglion. No.
Okay. So there may be, okay? But maybe they are sensory. You're right, maybe. Okay, so please pay attention to me. So I told you that nerve number 3, 7, 9, and 10 carry parasympathetic fibers, right?
Yes.
Where they are coming from?
Brainstem. Brainstem.
Yeah, brainstem. So nerve number 3 carries parasympathetic fibers from
With the brain.
which nucleus?
Edgar Westphal.
Edinburgh Westphal. Good. Nerve number 7 from
superior salivatory.
superior salivatory. Nerve number 9,
Dorsal.
inferior salivatory. Nerve number 10,
Dorsal nucleus.
dorsal motor nucleus of the vagus and ambiguous.
And because motor, doctor.
Yeah, it's motor.
Motor and parasympathetic.
Yeah, parasympathetic.
Please, a new information.
New information.
سجل على وسجل.
Okay. So let's compare. Let's compare again the somatic nervous system and sympathetic and parasympathetic. So somatic neurons go directly from the CNS to effector organ. Right? Please pay attention to me. I know that you're tired, but please attend to me. Parasympathetic nervous system is like this, right? So it originates from the CNS, goes to the ganglion, then from ganglion, postganglionic neuron goes to the effector. So pay attention to the length of the preganglion and postganglion. Which one is longer?
Preganglion.
Good. In the sympathetic nervous system, we have preganglionic neuron from the CNS that goes to the ganglion, and then from here they go to effector.
It's RC.
Yeah. But we have also preganglionic neurons that go to the adrenal medulla. They activate the adrenal medulla to secrete epinephrine and norepinephrine into the blood.
Exception, as you say.
Yeah. Then through the blood, they go to the effector organ. So the first part is the nervous system. The second part is in the circulatory system, right? Blood. One important thing. Here, acetylcholine is released, somatic nervous system. Parasympathetic nervous system. In the ganglion, acetylcholine is released. Sympathetic nervous system. In the ganglion, acetylcholine. Adrenal medulla, acetylcholine. So all preganglionic neurons in the sympathetic and parasympathetic nervous system release acetylcholine. Somatic neurons also release acetylcholine. For these, receptor is nicotine receptor. Right? So here we have nicotine receptor for contraction of the muscle. Here we have nicotine receptor for transmission of the signal from pre to post ganglionic neuron. Here we have nicotine receptor again. So acetylcholine is released and bind to the nicotine receptor. Right? Here we have also nicotine receptor. Okay, now, in the parasympathetic nervous system, on the effector, in the postganglionic and effector cell, we have again acetylcholine. But in the sympathetic nervous system, postganglionic neuron releases
Postganglion.
yes, postganglionic cell. Got it?
Yes.
Got it, doctor.
Good. Again, sympathetic nervous system, parasympathetic nervous system. In the ganglia, we have acetylcholine. Acetylcholine binds to nicotine. On the effector, postganglionic cell, in the parasympathetic nervous system releases acetylcholine. In the sympathetic nervous system releases norepinephrine. Receptor here is muscarine. Here is alpha or beta. Good. Exceptions. In the sympathetic nervous system, preganglionic neuron releases acetylcholine. Postganglionic neuron releases norepinephrine that acts on alpha and beta receptors, right? So sometimes we have some exceptions. Here, norepinephrine is released together with neuropeptide Y. Remember from the first session?
Yes.
We call this co-release, co-transmission.
We
Right?
remember this.
Two neurotransmitters are released at the same time. Right? Where do we have this? Blood vessel in the skin, skeletal muscles. Sometimes we have sympathetic neurons, but the postganglionic neurons releases acetylcholine instead of norepinephrine. Right? So,
Doctor, the last one?
last one. I told you that sometimes in the sympathetic nervous system, the postganglionic cell releases acetylcholine instead of norepinephrine.
It's more active, correct, doctor? Acetylcholine more active.
No, it's not more active. So the nature of the neurotransmitter is this, acetylcholine. So when I talked about this, I told you that postganglionic neuron in the sympathetic division releases norepinephrine. But it's not always the case. Sometimes acetylcholine is released.
Because the receptor of sweet gland is nicotinic receptor.
Yes? Okay. Acetylcholine is made by choline acetyltransferase. Choline acetyltransferase that make connections between choline and acetate in the form of acetyl-CoA. So we have acetylcholine, right? It is secreted. It remains for a few seconds. Then it is destroyed by acetylcholine. So choline acetyltransferase for synthesis. Acetylcholinesterase for degradation, for destruction.
For what?
For destruction. Now, norepinephrine.
Choline acetyl transferase for building acetylcholine.
Yes. Synthesis. And acetylcholinesterase for degradation. So, norepinephrine is made by L-thyroxine amino acid. So this one is hydroxylated by tyrosine hydroxide. It becomes L-dopa. Right? L-dopa is decarboxylated by dopa decarboxylase. It becomes dopa. So in substantia nigra, particle factor, each neuron has this enzyme and this one. So tyrosine is converted to dopa, and it ends here. There is no other enzymes for conversion of dopamine to norepinephrine and epinephrine. Right? But, for example, in the locus coeruleus, or in sympathetic postganglionic neurons, we have this enzyme, and this one, dopamine hydroxylase. Right? So dopamine is converted to norepinephrine.
No,
But in postganglionic neurons of the sympathetic nervous system, we don't have this enzyme. So norepinephrine is not converted to epinephrine. Norepinephrine is released. But in the adrenal medulla, we have that one, and also
this one.
So norepinephrine goes one step beyond, becomes epinephrine, and then it is secreted.
Doctor, in Parkinson's disease, it seems to be that tyrosine hydroxylase is absent.
No, neuron is lost.
Neuron.
The whole neuron is damaged.
Then if we give the patient L-dopa, which neuron can process L-dopa into dopamine?
Yeah. Got it. I don't.
Yeah, it's difficult to answer.
This is bio.
Maybe the remaining neuron.
Biochemistry, Doctor. This not physics.
I think with time,
No, it's pharmacology.
Doctor, we with time lose, for example, some enzyme like lactose enzyme, and at the same time maybe substantia nigra lose tyrosine hydroxylase.
But it's better to ask this from pharmacology professors.
Yeah.
They know this.
I think Dr. Shafi'i is good.
Dr. Shafi also maybe. So, removal of the norepinephrine, right? So it acts for a few seconds, then it is removed by one of these processes. Reuptake, diffusion, destruction. You know reuptake, right?
Yeah.
Yeah. So norepinephrine is released. So It binds to alpha receptors or beta receptors. It exerts its action, but there are some transporters here that brings the norepinephrine back to the cytoplasm. We call this reuptake. So 50 to 80% of norepinephrine is removed from the synapse by way of reuptake. The remaining norepinephrine diffuses away from the synapse, right? Or degraded by some enzymes. Which enzymes? Monoaminoxidase, catechol, O-methyl transferase, COMT. Catechol O-methyl transferase. So norepinephrine in the blood is also destroyed by enzymes. Okay, receptors. We know that acetylcholine has 2 receptors, right? Muscarine and nicotine. And from the first session, you know that we have metabotropic and inotropic receptors, right? Which one is inotropic here?
Where?
With nicotine or muscarine? Nicotine is an inotropic receptor, so it's a channel. Acetylcholine binds, opens the channel, ions can come, right? But muscarine receptor is metabotropic. It is coupled to G proteins, right? So they cause several actions by way of activation of G proteins. Okay. Adrenergic receptors include alpha and beta. Right? We have alpha 1 and alpha 2, beta 1, beta 2, and beta 3 receptors. So 5 adrenergic receptors. Norepinephrine has more action on alpha receptors, less action on beta. Norepinephrine. But epinephrine has similar actions on alpha and beta. So which one has more action on beta? Epinephrine. Which one has more action on alpha?
B2?
Norepinephrine.
No.
Right? Got it? Repeat? Yeah, I told you that. Norepinephrine mainly excites alpha receptors, but excites beta receptors to a lesser extent. Okay? So norepinephrine activates alpha more than beta. But epinephrine excites both types equally. So alpha is equally activated. So you want to activate beta receptors. Which one is better?
Epinephrine.
Epinephrine or norepinephrine?
No, epinephrine. Because
You want to activate alpha receptors. Which one is better?
epinephrine. No.
Right?
Doctor,
Yes?
in alpha receptors, okay, both epinephrine and norepinephrine are the same in strong in activation or no? Or norepinephrine is stronger?
Norepinephrine is strong. Because it's more specific for alpha receptors.
Yes.
Okay, so let's see the actions of alpha receptors and beta receptors. Alpha receptors cause vasoconstriction. Beta receptors cause vasodilation. So blood vessels are constricted. If alpha is activated, they are dilated when beta receptors are activated. Which beta? Beta 2. Right? Iris muscles. So they regulate, this muscle regulates the size of the pupil,
Yeah.
right? So activation of alpha receptors causes dilation. Good. In the intestine,
Intestinal relaxation.
alpha receptor causes relaxation, but causes constriction of the
Sphincter.
sphincter. So intestinal wall is relaxed,
The sphincter.
intestinal sphincter is closed, right? It is constricted. So motility decreases, material remains in the intestine, right? When alpha receptors are activated. Hair cells are activated by alpha receptors. Okay?
Yeah.
In the bladder,
Sphincter contraction.
the wall is relaxed. Wall is
And the
relaxed.
sphincter closed.
Yeah. And sphincter constricts. Uterus also is relaxed. Right? When activated by activation of beta receptors. So bladder sphincter is constricted. But activation of alpha 2 receptors decreases norepinephrine release. How? So postganglionic neuron releases norepinephrine, right? On the
Post side.
on the cell, so this is the effector. We have alpha cell receptors and beta receptors, right? So that this one is alpha 1 usually. So norepinephrine is released, binds to this one and activates. But we have also receptors here that are alpha 2. So alpha 2 receptors are presynaptic. Alpha 1 receptor is
Post.
norepinephrine acts on this one, and
This one.
alpha 2 is inhibitory.
Yeah.
So it inhibits the release of norepinephrine. So norepinephrine is released, it decreases the release of itself.
Beta.
Its own release is depressed, right? So it inhibits neurotransmitter release. Beta receptors cause vasodilation, cardio acceleration, beta 1, increase in heart rate. Increase myocardial strength, contractility, beta 1. So in the heart, we have beta 1 receptors to increase the rate and contraction. Beta 2 causes intestinal relaxation. It's similar to alpha. So in the intestinal wall, both alpha receptors and beta 2 cause inhibition. Beta 2 also cause uterus relaxation, bronchodilation, calorigenesis, glycogenolysis, beta 1 for lipolysis, bladder wall relaxation, beta 2. So bladder sphincter is constricted by alpha, bladder wall is relaxed by beta 2. Thermogenesis by
Beta 3.
so you want to increase heart rate, you need a medication. Which receptor can be targeted?
Beta.
Beta 1.
B1.
Beta 1, very good. You have a patient with hypertension.
B1, beta.
Beta
You
2.
want to dilate the vessel.
B2.
Sorry.
Right? You have a patient with hypertension, you want to dilate the blood vessels, but you don't want to use beta 2 receptors.
I did.
Increase the parasympathetic. Increase the parasympathetic.
Yeah, you can block alpha receptors, right? So you can activate beta 2, or you can inhibit alpha. Why you don't want to use beta 2 or beta receptors?
You don't activate the other.
Maybe
Activate other.
you don't want to hyperactivate the heart.
Yeah.
Because we know that in a hypertensive patient, the heart is under pressure.
And we have bronchodilation.
There may be also some side effects, right? Okay. You want to increase heart rate, but using an adrenergic drug is not allowed in this patient.
So low
Like
alpha
that.
receptor.
No, adrenergic receptors, alpha and beta, you're not allowed to use it. Because the patient has some problems.
Epinephrine or epinephrine?
Epinephrine, so epinephrine excites adrenergic receptors, alpha or beta.
Block it.
Blood what?
Epinephrine.
No.
Receptors?
Maybe you can block it, okay. But you don't want to use any adrenergic drug. Not activation, not blocking. So why don't you think about acetylcholine?
Yes, parasympathetic.
Yeah, parasympathetic,
If
they
we-
decrease heart rate.
Yes, we
Sympathetic.
want to decrease it.
Yeah, but you want to increase it.
Sympathetic.
Yeah, sympathetic,
Activate the sympathetic.
anticholinergic,
In this case, inject epinephrine.
epinephrine. No, I don't do it.
Stat.
You want to, for example, increase the heart rate, but you don't want to affect any of the adrenergic receptors.
We use acetylcholine.
Not acetylcholine itself, but you can use drugs that activate acetylcholine receptors,
Yeah.
Use any drug to
like atropine.
blockage the
So
adrenergic receptor. Use the another drug to
Another drug.
blockage the
Adrenergic.
adrenergic receptor.
I told you, you don't want any drug that blocks or activates adrenergic receptors. So,
I don't hear you.
forget the adrenergic
What's
receptors.
the effect of acetylcholine on the heart rate?
Decrease.
But you said we want to increase it.
Yeah, so you should use an antagonist of the receptor.
You said if we want to increase the heart rate,
Yeah?
we should inject the patient with acetylcholine
Not
or a
acetylcholine.
drug.
I told you should think about the drug that affects acetylcholine
Affects it.
receptors.
Antagonist to acetylcholine.
So effect here can be activation or inhibition. So you should use a medication that blocks acetylcholine receptors.
Okay.
Right? Heart rate goes up.
By which mechanism, please?
No.
Okay.
We don't know, but we must
So-
choose.
Please. You have heart. In the heart you have SA node,
Yes.
right?
Yes.
It may have alpha receptors, beta receptors, muscarine receptors.
Yes.
We don't want to use these.
Yeah.
Muscarine receptor is inhibited, right? So if you use acetylcholine or anything that increases acetylcholine, it will decrease heart rate. But you can use an antagonist. You should block muscarine.
We will increase the heart rate.
Yeah, alpha and beta are there. So there is a balance between the activation of this and this. When you remove this, alpha and beta can increase.
The heart rate. Thank
That's
you.
it. You're welcome.
When we
You want more questions?
Yes, we
It's
hope
okay.
that. Okay.
It's okay, yeah. So let's go ahead. So which way?
Yes, that's it.
This way. چقدر وقت داریم آقای دکتر؟ 30 ساعت. So
I'm not doctor.
let's see.
We are tired.
You're tired.
Yes, from the morning until now.
Doctor, continue.
Yeah.
Yes.
هلا وين الكونتينيو؟
Okay. So let's see the action of the sympathetic and parasympathetic fibers in some organs. Let's just start with the eyes.
Yeah.
You know that in the eyes we have iris muscles,
Yeah.
right?
Yeah.
That regulate the size of the pupil.
Yeah.
So we have circular iris muscle, radial iris muscle. What happens if this one contracts?
Vasoconstriction.
Pupil is constriction.
Yeah.
Pupil.
Yes.
So the
pupil
pupil
constriction.
size will be less, right?
Yes.
We call this meiosis.
And activated in parasympathetic situation.
Yeah. What happens if radial muscle is activated?
The size of people.
The size increases.
Alpha receptor.
Circular muscle is innervated by parasympathetic fibers. Radial muscle is activated by sympathetic. So, for regulation of the pupil size, both the sympathetic and parasympathetic neurons are important. And there should be a balance. Right? Again. Parasympathetic fibers activate circular muscle, cause meiosis. Size decreases. What is the receptor here?
Beta.
And
Alpha.
Alpha. Alpha 1.
Doctor, alpha for the dilation.
Why? Yeah, you're right.
iris dilation.
It's the first time that you're right.
Because the alpha,
Yeah.
alpha beta response for the parasympathetic, but the alpha beta for the parasympathetic. But
No, beta is not for parasympathetic.
because the previous slide.
Let me.
Because yes, iris dilation
Yes.
caused by alpha receptor.
Alpha.
Okay.
I say,
But not beta. Okay?
doctor, don't let me complete the answer.
Okay, I wait. Okay.
Yes, I said sympathetic can activate the alpha for dilation the iris, but the parasympathetic decrease the contraction of the iris.
Okay. By which receptor?
يمكن beta.
No, beta is not for parasympathetic. Muscarine is for parasympathetic. So the first part of your explanation is correct, but the second one, no. Right?
Don't consider Canada answer.
Doctor, in para.
Parasympathetic uses muscarine
دكتور محمد تعين على الجامعة
for meiosis,
صار شيء.
right? Because it's here in the circular muscle. Sympathetic stimulation activates alpha receptors that is here in the radial muscle. So it causes mid-reactions. So muscarine for parasympathetic, alpha 1 for sympathetic. Do you agree? Do you agree?
Yes, yes.
Good.
Hobby.
So, another muscle in the eye is the ciliary muscle.
Yeah.
Here.
Yeah.
So please pay attention to me. Please pay attention to me because if you don't listen, you cannot understand this, okay? So ciliary muscle actually keeps the lens in the muscle, in the eyes.
The cornea.